Hi, my name is Ayan and today I'm going to talk about Fermat's principle of least time. You will be surprised to know how a very simple theorem or principle can explain two very important phenomena related to light. One is reflection, which we already know, and another is refraction, which we already have seen in probably high school, right? So what is Fermat's principle of least time? This is basically a statement that when light goes from one point to another, it always goes through that particular path that takes the least amount of time. For example, we have a light source and we have a target. So what is the path for the least time? It's a straight line. It's a direct straight line, right? Very simple. But it's true in any situation, okay? This is true even if we have two different medium between the source and the target. It will let's take this example. Let's say we have a source which is in the left side, which consists of air, and in the right side we have another medium which is of glass, and the target lies there. So now I'm asking you the same question again. Which path will light has to take so that from reaching from source to the target it will take the minimum time? There are a couple of characteristics. In air, light will have high speed and less time because the refractive index is like 1. For glass, the refractive index is 1.5. That means it will have low speed but it will take more time. Okay, because we have a boundary between air and glass, obviously light has to take a transition. For example, this is one of the options that light can take for reaching from source to target. I'm showing you a couple of more options, but actually there are infinitely different paths that light can take, right? And we are actually interested in the path that will take the least time. Okay, so what are we going to do is that we are going to solve using Python this particular question. What is the algorithm that I'm going to use? I'm going to divide this boundary into 1,000 points. So each 1,000 point corresponds to a unique path from the source to the target. I'm going to calculate the total time required in each path, and finally I'm going to plot the minimum. So this is the code that I have written to solve this problem, finding the least time. Let me run this code. So we have two medium. Left hand side we have air, right hand side we have glass. We have a source and target. The light coming out of this source is orange, then it makes a transition, and this is green. Yeah, so we can move these objects using this grabber. So every time I move an object, whether it's light or it's a target, my code calculates the total time through each individual paths, each individual paths possible through this boundary, and it finally plots the minimum one. Now look how similar this diagram is compared to what we have already learned. We already know that light bends when it goes from a lighter medium to denser medium, right? So you see this bending. Now watch, something really cool is going to happen when I switch this object from denser medium to a lighter medium. So now light is traveling in the same medium, and this is a phenomena of reflection. And isn't this magic? Because my code doesn't care about reflection or refraction at all. My code just cares about finding the path with minimum time, right? So as you can see, this simple principle, finding the least, finding the path that takes the least amount of time, can explain both reflection and refraction. Isn't this amazing? Now I'm going to do something more interesting. I'm going to calculate the angle that both incident and reflected rays make on the common normal. And I'm also going to multiply that angle. I will take the sine of that angle and multiply with the refractive index. So basically I'm calculating n1 sine theta 1 here and n2 sine theta 2 here, which is basically, you already know, which is Snell's law. Now, isn't how interesting is that? You see, the Snell's law is valid at every point. It doesn't matter how I move these objects. Snell's law is always valid. It doesn't even matter if we are in refraction or reflection mode. In reflection, all these two angles are similar, so Snell's law becomes valid automatically. But you may be thinking, like, when you were in high school, you were given this formula, Snell's law, right? And even when I first learned about Snell's law, I had no idea like how it works. It was just a statement. But now, how crazy is this? Like, one simple phenomena, one simple theorem can explain both of them, and Snell's law is just a natural outcome. Thank you for watching. If you like this video, just let me know. If you want to know the Python code that I have, just comment. I'll send you. And thank you for watching.